In this session, we present a recent article called Control of Rough Terrain Vehicles Using Deep Reinforcement Learning. While deep reinforcement learning has seen plenty of recent success in solving various robotics tasks, less is known about its potential in controlling heavy vehicles in rough terrain. We use a forestry vehicle called a forwarder, which unlike conventional vehicles has 6 active suspensions. This makes the problem even more interesting from a control perspective. The goal of the controller is to navigate the vehicle from its initial state to a target pose, defined as a planar position and heading. The challenges include preferences on traversal to be safe, energy and time efficient, in terrain with high roughness with obstacles. As always in reinforcement learning, the environment is the world the controller lives in. It contains the vehicle, consisting of 37 bodies and 14 actuated joints, and the terrain, which is represented as a surface height map. The blue transparent cabin in the image shows the target pose. At every step, the controller specifies the torques of each wheel, the target positions of the cylinders in the suspensions, as well as the desired angle for both articulation joints. Together these form a 14-dimensional action in continuous space. The wheel torques are passed directly to the wheel motors, while the action for the suspensions and articulation joints go through dedicated P controllers. The low-level P controllers offload the RL controller by doing a lot of the underlying work before passing the output signal to the actuators. Given an action, the environment transitions to a new state with a set of observations. The observation contains information about vehicle configuration, its velocity, orientation, and the pose of the target. The haptic observations include the vertical force acting on the suspensions and the longitudinal and lateral wheel slip. The controller receives perceptual information from a local height map, which is seen in the video, follows the movement of the vehicle. The controller runs at 12 Hz and the simulation at 60 Hz. Its policy is represented as a multivariate Gaussian, where the means are parametrized using a neural network. The neural network processes the height map using a CNN before concatenation with the other observations. The concatenation passes through a feed-forward network which outputs the action. Due to some action, the environment also responds with a reward. The reward represents terms that dictate high-quality traversal in rough terrain. It promotes the controller to reach the target pose, maintain a level posture, distribute the ground forces evenly among the wheel, keep a low energy consumption, prevent wheel slip, as well as trying to avoid contact between the wheel sidewalls and the terrain. We use a 4-level curriculum and train the final controller for about 20 million steps. We now demonstrate learned skills on challenging terrains, including reconstructions for high-density laser scans on forest sites. On a side slope of 27 degrees, the controller fully extends the suspensions on the lower side while fully contracting those on the other. The shifted center of mass gives the stability to reach the target with minimal wheel slip. When obstacles appear in the local height map, the controller uses different strategies depending on the placement and obstacle in relation to the target. It chooses to drive around larger obstacles. For smaller objects, the controller finds it more rewarding to drive straight across. We observe the same behavior on 3D reconstructions from natural terrain with high density of large boulders, as the one seen in the current video. To simulate the controller in a typical forestry application, we place a sequence of targets that trace out a route. The route starts at a forest road and involves crossing a steep ditch. This is a challenging scenario that human operators may struggle with. The controller crosses at an angle and makes smart use of the suspensions before continuing to traverse the hill. The terrain is a 3D reconstruction from high-density laser scans of a harvest area outside of Sundsvall, Sweden. At the end of the route, the controller must cross the same ditch again from a different direction to return to the forest road. To study the domain sensitivity, we chose a terrain from the real dataset and varied the coefficient of friction between the tires and the ground, as well as the load. This figure shows the average normalized return over 40 simulations of various friction and 2 different load cases. The controller performs the best around its training setting. In general, the controller shows high performance in a wide range considering it has not seen such domain variations during training. This indicates that the controller has learnt robust control strategies. In summary, deep reinforcement learning is a promising method for end-to-end control in rough terrain concerning heavy vehicles. The controller learns to perceive, plan, and control with intelligent use of the active suspensions. Although testing on reconstructions of natural terrain presents all the traits required from a skilled operator, the DRL controller was never transferred to reality. A study of the sim-to-real transfer has already been conducted and is expected to be published in the near future.